Hello and welcome to episode 30 of Diabetics for Diabetics Radio. Today's episode is titled Iron and Stem Cell Health. We're going to talk about how iron impacts stem cell generation, stem cell differentiation, how stem cells work, how they proliferate, and how that impacts the diabetic state from both inducing diabetes as well as healing diabetes. If we haven't met yet, my name is Bowie. I've had type 1 diabetes for over 22 years, and I have been diving into the research for the past year and a half to 2 years looking for answers. Now, I have kind of started this community of individuals interested in healing the diabetic state and not being diabetic anymore. I found out that a lot of the information that was being shared by endocrinologists, doctors, was incomplete and based on a lot of outdated information. And so I've gone about to kind of collect all of the newest, shiniest stuff and put it to work and trial and error on myself. And I've been sharing my journey here on YouTube. Subscribe if you haven't already, as well as on TikTok. So, diabetes and stem cells, unrequited love story. Now, chances are, if you have diabetes, you have heard the word stem cell at some point. I remember being diagnosed in 2001, and stem cells were the new rage, right? They were regenerative medicine, the idea that you could take this cell that had the potential to be anything you wanted it to be, and you would be able to grow it, right? And that idea was so influential on me because it shaped what I wanted to go to school for. I ended up going for molecular biology, and I wanted to grow stem cells in petri dishes and see if you could grow organs and what have you. And this was such an important finding because it gave people with illnesses and diseases a chance to hope for growing something new, because we have been told that something is defective in us that grew something the wrong way, and now it's not able to be used properly. And so stem cells gave you this kind of reset button idea of being able to inject or grow this new tissue, this new organ, and kind of just insert it and return to normal, right? Stem cells themselves are sourced from all over the body. Initially, the main source of them was in undeveloped embryos, so embryonic stem cells. There have since been more sources. Bone marrow is one of them. From blood cells, you can actually de-differentiate cells, like take something that has already become, like, let's say, a liver cell, and activate a few factors within that gene or a few factors within that cell that cause it to kind of go back to a more fluid state, so it can become other different types of cells. But the idea is that for a diabetic, you would take these stem cells and then tell them to become beta cells. And then for the diabetics that are missing beta cells, here are the new beta cells. And so this has been an unrequited love story because we've been talking about it for a very long time, right? And there have been flashes in the pan of progress and of hope and of healing. Again, it has all been talk, very little application. 2021, there was this kind of like flash article in the New York Times about this man on the right, Brian Shelton from Ohio, who was part of a company's phase 1 trials in testing out stem cell treatment. And 270 days into that trial, he did not need any exogenous insulin anymore. And so it was this amazing breakthrough, right? Stem cells finally being able to bear fruit. And the phase 2 trial to increase the dose and the time to healing, what have you, it got canceled. it got canceled, and there have just been no updates. So again, I kind of feel like a fish looking for the worm on the hook, but it just keeps getting pulled away every time anybody ever gets close. So lots of promise in stem cells, very little application, meaningful application for people who would benefit from the stem cells. So let's talk really quick about how stem cells work. So pluripotent just means like very potent, multiple abilities to become multiple cells. So there are obviously different kinds of cell types: liver cell, heart cell, skin cell, nerve cell, and things like the beta cell. In the laboratory, there are a lot of different factors that go into what makes a stem cell grow into what it needs. Precursors like different growth factors, right? When most people think of stem cells, they think of some sort of chemical manipulation to, bathe the cell in something that is going to tell it to do this or do that. Cytokines are sometimes inflammatory markers, but generally just messengers in general. And there's also physical contact and physical force on the cell that is going to shape it and tell it where it is in the body and how to become what it's meant to become. So here's a great article, and the paper it came from, the paper is titled "Directed Stem Cell Differentiation, the Role of Physical Forces." So this paper focused on the physical aspect of how cells differentiate. Now, this was eye-opening for me because you can just see listed here physical forces, cell to ECM. ECM stands for extracellular matrix, which is like the space in between cells, and then actual physical cell-cell contact. So shape of cells has a lot to do with how cells know where they are and how cells know what to become, which I had never really considered. But, you look at like two cells kind of floating in space. This one is, let's say, a liver cell, right? This is the liver cell, and this is the stem cell. What the stem cell does is it actually touches that liver cell, says, oh, okay, this is a liver cell. I can tell by the shape of it. I know I'm in the liver. If I need to differentiate, I know that I need to become a liver cell. Now, there are a lot of different factors that are going on in the already liver cell that are going to let the stem cell know when to differentiate, what's going on in the environment itself, and, things like cell shape. These are two of the papers that I'm referencing. But cell shape, is it supposed to be a flat cell, kind of like long and striated like muscle cells? Is it round like a fat cell, swollen, compressed? Is it pulsing? Heart cells are obviously going to be a lot different than a fat cell, for example. And so it's pretty incredible when you think about it, because there's a lot more to it than a lot of people ever think to consider. Like we mentioned before, the growth factors, right? If let's say you're in a bone cell and you get erythropoietin or IGF-1, those are all kind of growth and regenerative factors that are going to tell stem cells to kind of get moving. But then the physical interaction with other cells, right? One cell knows it's in the heart because it is bouncing off of heart cells. It kind of figures out where it's at and what it needs to become. And then also from a health standpoint, cellular integrity. So if it's in a bone cell that kind of isn't healthy and isn't the right shape or the right density, it knows that it shouldn't differentiate, because it doesn't want to become, or it doesn't want to mirror something unhealthy, right? So it's able to take in environmental factors that are going to influence what it becomes. Another example is cyclic compression making muscle cells, right? So if you have stem cells kind of floating through your muscles, if it's you're constantly flexing and extending muscles, that cell is going to be able to feel that kind of compression and know what it needs to become, which is just so fascinating to me. And then I mentioned before, if a cell can tell that something is wrong in the cells that it's touching, is it worth differentiating and actually becoming part of a damaged tissue? Or is it time to just, apoptosis and call it quits and not differentiate because the cell isn't, or the tissue isn't healthy enough to survive? So the stiffness, the stretchiness, the swollenness, it is so fascinating. And it planted a seed for me to consider, well, what are the factors going on in the diabetic state that are going to tell stem cells what to do, So it made me think of Goldilocks and the Three Bears, right? Which the stem cell is trying to find the cell that is kind of at the right condition to allow for it to grow. It needs to know what it's going to be, and it needs to know if it's safe to become what it's going to be. So for those with diabetes, what are some conditions that we experience that could alter the cellular environment enough to impact that differentiation? So that could be chemical, right? What do we have flowing in our blood that would kind of alter the safety aspect of what stem cells seek? What are the structural changes, right? How are the cells of our body different, and how could that translate to stem cells either working better or not working at all? And they mentioned the word swelling. They mentioned the word swollen, and I immediately thought of inflammation, right? We learned that cell shape plays a role in how stem cells differentiate. Inflammation and swelling are things that are altering that cell shape. So when you have a regular cell and you have that kind of stem cell trying to figure out what it's going to be, if this cell is kind of like inflamed and out of shape, this stem cell comes along and is like, whoa, man, something's not right. I don't want to be this. You're going to have issues when it comes to getting those stem cells to kind of grow and become what you need them to. So are there things that we can do to influence an inflamed cell shape to promote proper stem cell differentiation? Not to mention the inflammatory markers, right? Like interleukin-6. There's plenty of other circulating, P38, I think, is another one, of these different growth factors or inflammatory factors that let the immune system as well as these stem cells know that something's not quite right. And once you consider all of those factors, how do you know what's affecting what? Again, I see the world in iron-tinted glasses because I have just become so fascinated with the omnipotence of iron in basically every aspect of diabetes that I've seen. So how does iron fit into this stem cell dysregulation? Iron creates a lot of reactive oxygen species, right? Are these reactive oxygen species disrupting the kind of chemical signals for stem cells? Iron is also very important in the formation of tissue and the formation of bone. So we talked about in episode 28 about diabetes and joint health, but iron directly impacts the mineralization of bone, both in slowing down the growth of bone, but also increasing the degeneration of bone and the resorption of bone. So those, affecting growth and upregulating, breaking something down doesn't bode well for stem cell, right? If stem cells are using that tissue health as kind of a sign of what it needs to do. And when it comes to cell shape and that effect on stem cells, iron causes the cell to swell, right? It causes all of those ROS. It has been shown to disrupt the shape and the membrane permeability of mitochondria and thus the cell itself. So there's plenty of ways that iron can insert itself into these roles that can disrupt stem cells. And I found this paper, and I have been absolutely smitten with not just the topics covered in this paper, but also the list of citations and resources and the branches that this has given me in learning more about chronic disease conditions, iron, and the resulting stem cell dysfunction. So I'm going to have the link for this in the description. I implore that you read this on your own, and comment what you read and what you learned. But this paper goes on to say that bone marrow stem cells are dysfunctional in many chronic diseases, specifically diabetes, beta thalassemia, and myelodysplastic syndrome, or MDS, which is a disease of blood formation, making blood. And it just kind of blew my mind as to how well documented these connections are. Iron and inflammation, inflammation on stem cell health, and its kind of feedback loop with iron regulation or dysregulation, as it were. It has just been so eye-opening. So we're going to dive into this paper here. I'm going to move my head over here real quick. And then, so role of iron and iron-related proteins in mesenchymal stem cells, cellular and clinical aspects. It's a 2021 paper. And talks about how iron plays an important role in stem cell health, both from a good standpoint, like iron is needed, but also in states of excess, what happens as a result to those stem cells. It is such a good, thorough paper. I'm a huge fan. It also, and I'm gonna spend some time here, gives a great overview of the nature of iron overload. So, important points to remember. Following dietary iron uptake by the enterocytes, so you can only absorb about 1 to 2 milligrams per day, gets absorbed into circulation where it binds to transferrin that transports it to the body, where the iron is taken in by the cells, used for all of the things that it's used for, which is a lot. Iron is an important molecule, right? Oxygen transport, the ETC in the mitochondria for making energy, bunch of different things. Now, in iron-loaded conditions, iron levels in the plasma exceed the iron bonding capacity of transferrin, which means that there's more iron than there is transferrin to bind it. Now, this can no longer be accommodated by intracellular ferritin, right? The iron just kind of keeps getting loaded, and the entry of the non-transferrin bound iron into the cells causes excessive intracellular iron. Now, the ferritin, which is the storage form of iron, can't handle the iron in the cell, and it becomes free iron because it's not bound to anything. Now, excess free iron accelerates the Fenton reaction, which we've learned about in previous episodes, and this increases ROS. Unregulated ROS is toxic and can directly damage protein lipids membranes and DNA, as well as other cell signaling pathways, right? And our body isn't able to get rid of iron effectively. And so this kind of just goes on for a long period of time, which is how we got to where we are right now. For starters, you're going to see the letters MSC throughout this paper. They stand for mesenchymal stem cells. Mesenchymal stem cells are a varied population of cells found in blood. Bone marrow is BM, liver, heart, lung, gut, skin, tonsils, adipose tissue, just all throughout the body. There are these cells that are able to kind of differentiate into a lot of different cell types wherever they are regionally in the body. And there's actually a really good diagram here that talks about where these stem cells are and what they're able to be differentiated into, which is good for people to be able to visualize. Now, how do we figure iron's role in all of this? Because, again, iron is very important. It's really a matter of quantity and whether or not you have the tools to handle it. So, stem cells have physiological and therapeutic significance, and we have to know how they use iron, as well as how iron can dysregulate the stem cells, right? So the dysfunction of stem cells is not just in blood-borne diseases. They mentioned beta thalassemia and MDS before. It also happens in liver, brain, and metabolic syndromes, okay? So this isn't just blood-borne stuff. This is bone marrow stem cells have been described, dysfunction has been described in beta thalassemia, diabetes, and MDS. And it mentions that it could be due to iron loading. There's a lot more later in the paper that talks more about those connections and how pertinent and possible they are. So let's take a look at this graph. Now, we're looking at the component of the cell and the effect that iron has on that component, right? So reactive oxygen species, plenty of research, all saying that iron loading in the stem cells increases ROS, no elevation, so maybe no change to ROS, and then elevation in the NOX4 protein levels, which is an inflammatory marker. So it's showing increases in the presence of ROS in iron-loaded tissues. Same goes for intracellular iron and the labile iron pool, which is basically the volume of free iron in the cell. Obviously, you load it with iron. It's correlated with the volume and the time that the cell is in that iron solution. So the longer it's in there, the more iron it's going to retain, right? And so they're looking at the labile iron pool for people with different conditions, things like beta thalassemia, in which they do have high iron accumulated in those stem cells. And having that iron is going to increase that availability of redox reactive iron, which is the main determinant in the cellular oxidative stress, right? So the more intracellular iron and labile iron pool, the more potential there is for oxidative stress. And then when you talk about ferritin, what are the effects of iron loading on ferritin? Iron-induced upregulation of ferritin expression, accumulated ferritin in the stem cells. Expression of light and heavy chains was lower in stem cells of beta thalassemia patients than healthy subjects. And you can see here from just this citation over here, light and heavy chains refers to the integrity of the tissue that it's forming. So the expression of the chains within the tissue was lower. And then treatment with exogenous ferritin, this is interesting. So giving ferritin caused an anti-osteogenic effect. So this is against the formation of bone by giving more ferritin. Interesting. And then another table talking about the impact of iron loading on the processes and activities of these stem cells. So the viability of the stem cells themselves. Iron loading reduced cell viability, cell death, increased cell death, no apoptotic signal, so that's a good sign, and then an increase in stem cells from iron-loaded patients with MDS, right? So those with those blood disorders are having more cells die off. An arrested cell cycle, so those cells aren't able to grow. High percentage of cells in the S phase, indicating high rate of cell division. This is an interesting one here because you may read, oh, okay, so the cells are in their S phase of division, which means they're dividing, which is a good thing, right? We want cell growth. But when you look at the actual paper itself, iron overload enhances stem cell growth, but hampers matrix calcification. So it's building bone, but it isn't calcifying properly. So again, that has to do with the tissue integrity, which we learned earlier is not a good thing when it comes to stem cell differentiation. And mitochondrial physiology, so fragmentation via ROS-dependent process, altered mitochondrial morphology and function, inhibition of mitochondrial fusion-fission, increased mitochondrial fragmentation. Clear to see here that the iron loading is having a very, very adverse effect on the health of the stem cells and all of the things that are benefiting from those stem cells. So here we expand a little bit on how iron affects reactive oxygen species signaling and its effect on stem cells. So, I mean, this whole first paragraph is just loaded here. So, iron treatment increases ROS production in stem cells, which positively correlates with labile iron pool, which just means the amount of free iron available, which leads to oxidative stress. ROS is not only a byproduct of cell metabolism, which is normal for mitochondria, but it's also a participant and modulator of many pathways. Hence, when there is too much iron and therefore too much ROS, it affects several cellular functions and involves multiple pathways. For example, iron loading in the stem cells leads to unregulated reactive oxygen species, which increase apoptosis and decrease cell viability. They go on to talk about, specifically in the formation of bone, regulated levels of ROS mediate osteogenic, which is bone growth, differentiation of stem cells, while excess iron-induced ROS elevation is anti-osteogenic, anti the growth of bone. It also talks about how iron affects the expression of foxhole proteins or FOXO proteins. They're transcription factors that activate genes to mediate apoptosis and cell cycle arrest, offering protection against oxidative stress. So if a cell is experiencing too much oxidative stress, the FOX proteins are able to kind of kill that cell off and prevent it from spreading its toxicity. So therefore maintaining the stem cell pool. Now, activation of this signaling, the foxhole signaling, involves downregulation of FOXO, which reduces that transcription, resulting in increased ROS levels and enhanced sensitivity to oxidative stress. So essentially, iron is disarming the protective signaling pathway that prevents the spread of ROS. And so when we look at this, and you take all of those factors into account for the role that iron is playing for those stem cells and the pathways influencing those stem cells expression, you get to see a lot of different things, right? And you can kind of delineate how impactful this really is for healing, as well as the development of the disease state, because we found pathways for proper growth and limiting damage are inhibited, right? It's not just a matter of stopping things from being broken down. We're also having to stop things from stopping what's doing the healing, right? It's working from both ends. It's stopping growth and it's preventing regeneration. So it's something we've got to pay attention to. Now, this top point, stem cells taken from diabetic did not grow to size or rate of those from healthy individuals, is actually being taken from a paper. You're not going to believe its title. That's right. Mesenchymal stem cell dysfunction in diabetes. This is a 2018 paper, and it talks about how stem cells being taken from diabetic people, when they are grown in the lab and grafted to differentiate into different cell types, they do so at a much lower rate than those in healthy individuals, which is huge on multiple fronts from both a natural healing standpoint. So you can be, for those interested in kind of growing their own stem cells and wondering why beta cells aren't regenerating properly, it's because in this inflammatory state, stem cells don't work as well, right? And again, going back to those factors before of what influences differentiation of the stem cells, if a cell is inflamed, that's a sign for the stem cell not to become part of its environment. And also from a procedure and a cure standpoint of having stem cells transplanted, it's pretty clear that the conditions leading to a diabetic state are the exact same conditions that kill and prevent the proliferation of stem cells. So if we're injecting stem cells into an inflamed body, that's not good, right? They're not going to be able to thrive and differentiate the way that we need them to. So let's take a deep breath. Let's look back at everything that we just talked about. So we've learned initially that in stem cell differentiation, they are extremely sensitive to inflammatory conditions, things like altered chemicals in the signaling pathways, in the physical stress on the cell, whether it be swelling, whether it be the integrity of the cellular membrane. We have also learned that iron plays a direct role in influencing all of those inflammatory conditions impacting stem cell health, right? And it's impacting stem cells' ability to differentiate. It's also impacting the area where those stem cells are coming from. Bone marrow is where a lot of stem cells are derived. Iron plays an important role in the proliferation of bone health, in promoting breaking down bone as well as preventing the growth of bone, right? So it's not just, our stem cells aren't able to work as well. It's there aren't as many stem cells. The total volume is going down. And then lastly, specific to the diabetic condition, diabetics who have a documented relationship with iron and excess iron causing a loss of insulin sensitivity, they also have documented decreases in their stem cell viability. So their inability to regenerate, their inability to grow new blood vessels, grow new tissues, and remain healthy. I mean, think about the diabetes and wound healing, right? We just kind of always assumed, well, it's an your immune system is affected. That's why wounds don't heal as quickly on diabetics. It's because your stem cells aren't able to differentiate effectively, right? And you're kind of like, things are moving a lot slower, and you're not able to heal as quickly. Now, can this be applied to healing? Not just wounds, but also beta cells? Why wouldn't it? So you would think regulating iron through offloading the excess iron and promoting the things that are going to help iron get recycled would positively impact stem cells' ability to grow, right? To have more stem cells, as well as those stem cells' ability to differentiate into what the body needs, which are beta cells.